and joined ISI Kolkata and did his, for whatever work he did there, got the PhD. Of course, degree giving body was Jadavpur. And as of present, he's an associate professor at Cryptology and Security Research Unit at what is called as RC Bose Center for Cryptology and Security. It's within ISI Kolkata. And there are, I saw a big list of postdoc positions and awards which I didn't want to go through. It'll take over too much of this time. So I'll hand over to Gautam Pal. So go ahead, please.
Hello, and I think, am I audible?
Audible. A lot of traffic.
Okay. Yeah. The main road is just outside the institute. So let me share my screen. Okay. The slides are visible, right? Okay, good. So, yeah, in the interest of time, I will limit my talk within 30 minutes, and then we can take questions because we wait. Okay. So, the okay, 1 second, let me just. Is it better now?
No, sir, it's noisy.
Slightly better.
1 second. See if this works. Hello.
Yep, best, fantastic.
Yeah,
this is good.
it's better. Okay. No, and I turned off the fan and the AC also, so they're creating a lot of noise. Anyway, so the topic is quantum secure direct communication protocols, and it's a joint work with one of my PhD student, Nayana Dash. Okay, so we'll after introduction and background, we'll look into some quantum secure direct communication protocols and the MDI version of that, and an extension to quantum dialogue and quantum conference protocols. Okay, so we know that quantum cryptography provides unconditional security based on the fundamental principle of quantum mechanics, mainly Heisenberg's uncertainty and the no cloning theory, right? And the first quantum cryptographic protocol for practical usage is BB84, which is a QKD protocol, quantum key distribution protocol. So QKD essentially is a protocol whereby two distant parties share a common classical secret key for future classical communication. Okay, so it's called quantum key distribution because the key distribution mechanism uses quantum principles, but the key itself is classical. Now, on the other hand, quantum secure direct communication that sends the message directly without the key. We know that in classical cryptography, sending a secret message always requires a key. Right? So in quantum, in classical secure direct communication, that means the classical analog of this, like if we say something as CSDC or classical secure direct communication. Because of the term direct means the message goes directly without key. So that thing cannot happen, because in classical channel, the people can copy the data, do the analysis, offline analysis, online analysis, and other things. But quantum encoding, quantum superposition, and quantum uncertainty, quantum no cloning, all these things together, they provide a facility through QSDC, whereby it is possible to send the message directly without the key. And we have predefined encoding and decoding rules for that. Okay. So one thing I would like to point out here is that this QKD and QSDC, one might think that they are quite similar, because ultimately at the end of QKD also, some message is being shared between them. That message happens to be the secret key, the classical secret key, right? But one very subtle difference is that in QKD, the choice of the message is not under control of either Alice or Bob. That means neither the sender nor the receiver can choose the exact bit sequence that will be established in the end. Right? One party generates a random or a pseudo-random bit sequence. Then through that protocol, some of the bits are discarded due to reconciliation, error correction, noise estimation, privacy amplification. So then finally a reduced subset of those initial random bits are actually shared at the end of the QKD. So a priori, before the protocol, the sender and the receiver cannot decide what bit sequence they are going to share or they are going to establish in QKD. Whereas in QSDC, because it is ultimately a message transmission protocol, so the sender and the receiver, the sender has to decide what message he or she wants to transmit, right? And whatever deterministic message the sender wants to transmit, the exact bit sequence, that should be recovered by the receiver. So that's kind of a challenge. Otherwise, if it was just sending something random, if the sender wants to send some random data, then actually the QKD can be used as a QSDC protocol, right? But for practical purpose, often we want to transmit the dynamic data. It's a dynamic communication that is happening between the sender and receiver. So we want fixed message that the sender wants to send to the receiver, a deterministic message, and therefore is the requirement of QSDC. Okay. So basic idea of QSDC in 2002, Long and Liu in their physical review A paper proposed a theoretical QKD scheme using EPR pairs. And it was designed for actually key distribution, but the key was prepared before it was sent. So that is important. So they actually did not call this protocol as QSDC protocol. It was a QKD protocol, but because the key was prepared before it was sent, so we consider it to be the seminal paper on QSDC. So it's possibly the first paper on QSDC protocol. And then in 2003, Deng and Long proposed the first secure model for QSDC. Okay, so the protocol, this is of the seminal paper, goes as follows. So they simply divide the message sequence in 2 bits at a time. Then the encoding rule happened into bell pairs, like 0, 0 goes to 5 plus, 0, 1, 5 minus, 1, 0 shy plus, and 1, 1 shy minus. So the EPR pairs are prepared corresponding to pairs of message bits, and then the EPR pairs are divided according to 2 sequences, QA and QB. So Alice keeps QA and sends QB to Bob to check the security of the channel. Now, if there is no eavesdropper, then Alice sends QA to Bob, and he measures each pair of Q bits, one from QA and another from QB in bell basis. So they are like synchronized, the ith Q bit in the sequence QA and the ith Q bit in the sequence QB They are kind of synchronized. And from the measurement result, Bob gets the message. So it's a very simplistic protocol. It does not assume any eavesdropper is present. Okay, so there is no security issues as such. So today we have many variants of QSDC protocols. Of course, we'll touch upon some of them and give references so that if anyone is interested can look into the details. So the basic requirements of QSDC, the state-of-the-art QSDC, is as follows. The secret message should be read out directly by the legitimate user. Okay? No additional classical information is needed to decode the message. That means once the receiver receives the qubits, right? Then the receiver will perform some measurement according to the protocol, and based on the measurement output, the receiver will interpret, right? But from the sender side, additional classical information is not needed as it is required in, say, teleportation or other kind of protocols. Right? So the secret message should not leak even if may get hold of the channel, right? So that's the security requirement. Okay. Now, very close to QSDC protocol is another kind of protocol which is called DSQC protocol, or Deterministic Secure Quantum Communication Protocol. Now, interestingly, that many papers in this area, they don't differentiate between QSDC and DSQC protocol. And often some protocols are actually DSQC protocol, but they claim that they are QSDC protocol. However, there is a subtle difference between the two. So the seminal paper on DSQC was proposed in 1999 PRA by Shimizu and Imoto. And the difference is that the parties need to exchange classical information to decode the secret message after the security check process. Right? So in short, no classical information exchange for QSDC protocol. However, for DSQC protocol, classical information exchange after the security check is over. Okay. So, and here, I mean, this is kind of not so impractical because the classical resource is definitely cheaper than quantum resource, right? And let's look at the first DSQC protocol, just like we looked at the first QSDC protocol. So let's look at this. The sender Alice sends encoded qubits to a quantum channel to receiver bot, and after the security check is processed, Bob measures the entangled pairs in Bell basis, and Alice announces the classical information about the encoding basis. So here, the encoding information is sent later. Okay. So from the announcement, so and Bob can actually map that what encoding was used for what information, right? So, for QSDC, similar thing can be done by a priori fixing the mapping, but here the mapping information is to be sent. Okay, so these two are kind of interesting variants, or you can call it extension of QSDC protocol. One is called quantum dialogue, and the other one is called quantum conference. So a quantum dialogue, or a QD, is just a bidirectional QSDC protocol. Again, the seminal paper in this was in 2004. A process. This is kind of a duplex version of the quantum security communication protocol. Because why it is called quantum dialogue? Because it uses the same channel. The single channel which is used to send information from Alice to Bob is also used to send information from Bob to Alice. Okay, and the quantum conference, QC, is actually a multi-party extension of QSDC. Okay, so we have one sender N receiver version, and we also have N sender and N receiver version. So that was proposed in 2019, and we also have one protocol in this direction, which we'll discuss later. Okay, now MDI, what is MDI protocol? Okay, so measurement device independent protocols, they are a class of protocols where all the measurements are done by a third party. This third party can be untrusted, and the idea is that by doing this, loopholes in the measurement devices can be eliminated. So we can assume that our measurement devices might have some loopholes, or they might leak secret information to the eavesdropper, right? By modeling the protocol in the MDI format, we can ensure that even if the measurement devices have some hacks inside them, but the protocol will be designed in such a way, maybe through some redundant qubits, some redundant steps, such that after the end of the protocol, it will be secure, right? So Alice and Bob will know that whatever they wanted to achieve has been achieved without leaking. So that's this MDI is actually a generic paradigm. It applies to many quantum communication protocol. It can be applied to QKD. There are QKD protocols which are MDI. There are QSDC protocols that are MDI. There are other kinds of quantum protocols in the quantum internet, quantum distributed computation scenario. Those can be MDI. Okay. Okay, and briefly, we want to identify the authentication problem, because any quantum protocol in the communication channel, right, requires authentication. What to speak of quantum communication? Any classical communication also requires authentication. So the identity authentication is a key requirement of security, right? Whether it's a classical protocol or it's a quantum protocol. Now, for the classical scenario, public infrastructure provides an authentication mechanism by a trusted third party, which is kind of a certificate authority, right? Which uses a certificate to an user and assists the other users to verify the certificate. Now, quantum authentication can be done, authentication in the quantum protocols can be done in many ways. One way is by using a trusted third party, which helps each of the legitimate parties to check the identities. So kind of each legitimate party will be registered to the third party and they can validate their identity. That's kind of a simplistic model, analogous to the classical one. Second one is by using a pre-shared short initial key. So so it's like a protocol for key growing rather than key distribution. So you have initial short key. Now you want to set up a longer key. So the short initial key can serve as authentication because they can match. Like one party can, send, the other party can verify, sort of that. So the third one is actually the real quantum protocol using previously shared entangled state between the legitimate parties, right? But it is costly, first of all. Also, the resource requirement is quite high because you need entangled states, and also that need to be shared. So it's kind of some meta protocol needs to be established before your current actual protocol, so that these entangled states are already shared between the parties. So a solution is that in one of the ways you can achieve authentication in QKD. And for other communication protocols, participants can use an authenticated QKD to generate their private authentication identities. So most of the authenticated protocols work with authenticated identities and how to generate them. In classical, we use classical key distribution protocol to generate those authentication identities, but in the quantum scenario, we can use a quantum authenticated quantum QKD. Okay, so that applies to any quantum communication protocol, not particularly to QSDC, but just mentioned it because QSDC is one prominent application of quantum secure communication. So here also this issue will arise. Okay, so once we assume that we have authentication in place, we have the resources in place, and now we can go for the variants or the different versions of QSDC. Okay, so now with this background where we discussed the what is QSDC, what are the different variants of QSDC or different extension of QSDC, and how the seminal protocols are designed. Now, since we have looked them into details, we'll now briefly go over some new protocols or some modified protocols that we have designed and what are their properties. So I would like to just highlight them. So the first one in this set is quantum secured rate communication using a single basis. Okay. So most of the quantum cryptographic protocol use either entangled state or single qubit states randomly prepared in a pair of orthogonal bases to transmit the information securely. We propose a QSDC protocol with user authentication by using only one orthogonal basis of single qubit states. So Alice chooses an arbitrary basis to encode her secret message. Okay. So the idea is as follows. Alice and Bob, they have k-bit identities, IDA and IDB. Let capital theta be a predefined set of angles with cardinality capital N. So, for example, theta can be one of the 360 values in degrees. You can have it in radian also, doesn't matter. The unit doesn't matter here. All it matters that it is a finite set. So capital theta can be chosen as per the user's choice. Now for each angle in that set theta, we can have an unitary matrix defined u theta as follows. So this is kind of a rotation matrix, as you can see. So u theta acting on the 0 qubit will produce cos theta 0 plus sin theta 1, and u theta applied on bracket 1 will produce minus sin theta 0 and plus cos theta 1. So the protocol is as follows. Suppose Alice's secret message is M that she wants to transmit to Bob. So she encodes M as 0 goes to u theta 0 and 1 goes to u theta 1 and prepares the qubit sequence. Let's call it QA1. Okay. After that, she prepares other qubit sequences, namely IA, IB, Q theta, corresponding to IDA, IDB, and theta. Okay. Now, they insert IA, IB, Q theta in QA1 and sends to Bob. Now, Alice and Bob will authenticate each other using IA and IB. Bob will get the value of theta from Q theta. Then he will decode the message M by measuring the qubits QA1 in u theta 0 and u theta 1. Okay. So there are some security analysis and some possible attacks on the protocol. So we have discussed how to resist those attacks and how the protocol is secured. The details is in the archive. Okay. Next. So there is a QSDC protocol by Yan et al. with mutual authentication. They use single photon and EPR pair, but we have shown that it's not secure again intercept resend attack and impersonation attack, and you can get the full secret message. And we modify the protocol. Okay, so the intercept resend attack is like Alice sends the quantum state to Bob. Eve intercepts those from the quantum channels, measures the state, and resend those to Bob. Okay? An impersonation attack is Eve impersonate Bob to acquire the secret message of Alice. And on the other hand, Eve impersonate Alice to send a wrong message to Bob. So the protocol is, okay, yeah, this is the modified version of the protocol. The Alice has n-bit message M. She prepares the qubits SMI, let's say, corresponding to MI. MI is the ith bit of the message. The encoding rule is if MI equal to 0, then the SMI, the encoded qubit, will be 0, 1 or 1, 0 with equal probability. And if the ith message bit is 1, then the SMI will be 5 plus and 5 minus with equal probability. Now note that here for one classical bit, we are having 2 qubits. So this is kind of a resource heavy protocol. And Bob measures SMI in Z cross Z or Bell basis, and then he decodes the message. So the decoding rule is summarized here in this table. The secret message bit of MI, encoded qubit SMI. So these are the possibilities. Then basis chosen by Bob, measurement result of Bob, and the decoded secret bit of Bob. We see that there are 4 possibilities of 0 decoding at the Bob side, and there are 4 possibilities of 1 being decoding at the Bob side. So if one marks out the math, it just perfectly matches. Okay, then there was a MDI QSDC protocol by New et al. In 2018 using EPR pair and entanglement swapping, and we show that there is insecure against information leakage. Basically, the untrusted third party gets half of the secret key without any active attack. Now, of course, we don't go into the details here. We modify both the protocols. So give the modified version, updated version as follows. So let's ABC. It's an MDI version. So let's recall that in MDI protocol, we need a trust party, a third party. And because the third party can be untrusted, we call it UTP. Right? So ABC stands for Alice, Bob, and Charlie. Charlie is the UTP. So here, I think it's the the diagram is pretty small, but I think the colors are visible, so we can have kind of a bird's eye view of what is happening. So the orange and the blue circles represent psi plus and psi minus respectively. Alice encodes 0, to identity, 0, to sigma x, 1, to I into sigma y, and 1, to sigma z. And Bob applies identity or sigma x randomly. So from the measurement result by UTP, Bob decodes Alice's secret message. So, okay. So yeah, so the table is quite long because there are a lot of possibilities. But if you go through this paper, you can see that all the rows of the table at the end actually correspond to the correct message bit that was intended from Alice's end. Okay, now we talk about the extensions of quantum secure direct communications protocol, like those are quantum dialogue and quantum conference. So in 2017, the first MDI quantum dialogue protocol was proposed. We proposed 2 modified versions of that. So the protocol is okay. So let's look at the protocol. So Alice sends Alice. Suppose the secret message of Alice is A1, A2, AN. So it's an N-bit message. They prepare a set of qubit QA to encode A and sends QA to UTP. Bob has a secret message B, B1, B2, BN, prepares a set of QB to encode B, and sends QB to UTP, the untrusted third party. Okay. Now the UTP measures each of QAI and QBI in Bell basis, announce the measurement result. So if the measurement, the ith measurement can be one of phi plus, phi minus, psi plus, and psi minus because it's in Bell basis measurement. Now, the UTP can get AIs or BI if MI belongs to phi plus and psi minus. So this is the attack on the protocol, this step. We showed in the original protocol, this Alice's bit sequence A and Bob's bit sequence B, though the attacker cannot decode either Alice's bit sequence or Bob's bit sequence, but the attacker has knowledge of the XOR of the 2-bit sequence. So that's an important information. Information theoretically, it's equivalent to kind of 1 bit per 2-bit of information. So because if given the XOR linked AI XOR BI, if somehow the attacker is able to guess AI, then the BI will be revealed with probability 1. Or if the attacker is able to guess BI, then AI will be revealed with probability 1. So the entropy of 2 qubits actually gets reduced to 1 bit. The entropy of 2 bits gets reduced to 1 bit. So that's the security leakage. And it happens 50% of the time. We see that because there are 4 equally probable outcomes due to the Bell basis measurement: phi plus, phi minus, psi plus, and psi minus. And we have 2 possibilities where the information is leaked. So these 2 out of the 4 possible outcomes will happen 50% of the time, right? So 50% of kind of positions are leaked. So Alice and Bob can decode BI and MI from BI and AI from MI, so that's not a problem. They will keep AI and BI if MI belong to phi minus or psi plus, and they will discard AI BI if MI belong to phi minus and psi minus. So that's the avoiding protocol. So this is suggested by us. This is the modification that we suggest in the original protocol, that Alice and Bob, they have the knowledge of MI, right? So if they detect that MI belongs to the danger set, phi minus and psi plus, then they will, the opposite, the phi plus and psi minus, then they will discard. Otherwise, they will keep. So this is kind of avoiding the protocol, avoiding the leakage by sacrificing half of the qubits. Alice and Bob use some classical function to choose such MI. Okay, yeah, so that's fine. Now, the quantum conference. So, generalized version of quantum dialogue is the quantum conference protocol, and what we have done is first we have generalized to a 3-party quantum conference by using an untrusted 4th party as the kind of the MDI guy who will perform the measurement, right? And then the same thing we have extended to an n-party quantum conference protocol by using the n plus 1th guy as the untrusted 3rd party. Okay, so this is the protocol. There are n parties P1, P2, Pn, n greater than or equal to 3. Each party Pi wants to send his message to the other n minus 1 parties, right? So let the m bit messages of Pi be capital Mi, and they share an small m bit key k, k1, k2, kn. So the encoding rule is as the previous MDI QD, which we had discussed. Send their qubit sequence to Pn plus 1. Pn plus 1 measures each n qubit states in Bn basis. Bn is the generalized Bell basis. Okay. And Pn plus 1 announces the results publicly. Each Pi prepares another sequence of qubits, sends it to Pi plus 1 mod n. So here, P1 sends to P2, P2 sends to P3, P3 sends to P4, like that in a ring structure. Then Pi plus 1 mod n measures those qubits, sends it to the next party circularly. Repeat this process n minus 2 times. Each Pi gets other n minus 1 message from the other n minus 1 parties. So, of course, this is a little computation heavy. Okay, but we can show that we can use this protocol to actually do some multi-party computation. For example, XOR computation. So if each party has an m-bit message Mi, then they can compute M1s or M2s or Mns securely, such that their numbers remain private. Okay? And they can take the help from the untrusted n plus 1th party. Okay, so basically we gave a brief overview of different variants of QSDC protocol, QD protocol, and QC protocols. And of course, it's not possible to go into the detailed security loophole or detailed security prevention mechanism of each protocol, how it happens. So the purpose of this talk was to kind of give a glimpse of how this protocol kind of look like, and kind of what are the operations, what are the choices, how the measurement is done, how the interpretation is done. So to give an overview of that, for details, definitely you have to look into the papers. Okay, so I would like to stop here and take any questions or comments.
Yeah, thanks, Gautam. Thanks a lot for this nice talk. So, participants, questions, you can unmute and you can start with it. Suresh, I'll talk to you later after half an hour. Suresh, I'll talk to you after half an hour. Huh? Right. So, maybe I should start with the questions. So, in all these protocols, are you encoding with more than one qubit per bit for a classical bit? Because in one of them you are doing it that way.
Yes, so so now in some protocol, if it is kind of noiseless, or you consider that there are no adversary, then it may be possible to use less than 2 qubits per
Okay.
classical bit. But of course, yeah, you are correct. If we want to ensure security, then definitely we have to do the expense. That's like in QQD, normally it's 4 times, right? So in order to send n bit
Right.
secret key securely, you need 4 times that. So in QSDC also like that. Sometimes it's much more, because it's a fixed message. You want to have more security than a random message. Right?
Right. So
So
basically,
that cost you have to.
it as a bit flip, you will consider it as some noise included or something. So it's something
Yes, yes.
security. You mean to say?
Yes. So here we have not considered error correction. For error correction, you need some more redundancy. But
I was not
here
looking
kind
for correction. I was only looking for the Eve's
e-
signal
error detection,
error detection.
and maybe discarding the protocol. Right, right. So for that, definitely you need redundancy.
Right. So anyone else? I'm sure there will be questions, but
Yeah, people can send me email if you can find the questions later on.